Assalamu alaikum and welcome to Digital Control System Lecture 1 Introduction. So recall, in control system, the following feedback configuration is used. So I'm having here comparator where I'm comparing the reference point with the actual output. Then I need to minimize the error signal. Here I'm generating the error signal. I need to minimize the error signal using a controller or filter or a compensator. Let's call it controller. The controller will give me U of t, the actuation signal, which will go to the plant. Now the plant can be pilot landing aircraft, for example, a servo drive system, robotics control system. And this is the output, Y of t. Let's assume here I'm having a sensor in order to measure the output, and I'm feeding back the output here. So this will be a sensor. So this is a classical closed loop configuration in the continuous time domain. So this is an example of closed loop continuous time control system. By continuous we mean that all the signals are known all the time. So simply here R of t, Y of t, E of t, U of t are known all the time. So all the signals in continuous time system are known all the time. However, recall that nowadays, if I need to implement the controller, I will implement it in the digital platform. So nowadays, if I need to implement the controller will be implemented in digital platform. So here will come the concept of discretization or the digital control system and why we need to study the system in a digital platform. So if we replot the closed loop configuration, assuming that I will implement my algorithm in digital platform or digital computer. So let's assume this is the reference generated inside my program. Here is my controller, and this one I will call it the digital filter. Of course, you can call it controller, compensator, controller, it will be the same. Now I need to connect the output of the controller to the plant. Remember that the plant is continuous time domain, which accepts a continuous signal. Let's assume that. So here I need to do an interface between the digital control or the digital platform, let's say, and the continuous time domain. So to do so, I will use an analog to digital converter to convert the signal from digital nature to analog nature, so I can connect it to the plant. The same thing here, I will measure the signal, then I will pass it through analog to digital converter. I will do discretization for this signal, and now I can complete my block diagram. So here I can assume this is a R of K, let's say Y of K. Here I'm having U of K, and this will be U of T, and here is E of K, which is a discrete time system. So this part of the block diagram is implemented in digital platform or inside, let's say, a computer. So this is an algorithm in digital computer, let's say, or digital platform. So the signal from here to here is discrete, and the signal in the red part is continuous, and the analog to digital converter or the digital to analog converter interfacing the digital domain to the time domain and the time domain to the digital domain. So here AD is standing for analog to digital converter, while DA is standing for digital to analog converter. Of course, I can have another configuration. One of them, for example, I only introduce, let's assume that I'm doing the comparison in time domain, so this would be R of T. This is Y of T. Here is E of T. Now I'm doing the digitalization here. So the first thing I will see is the analog to digital converter. After that, I will implement my controller. So this is the controller. Let's assume it is C of Z, and I'm using Z to represent the Z domain or discrete domain. So this is the digital controller. After that, I'm generating here U of K, so I need to convert it to analog signal. So I will use the digital to analog converter. and here I'm having u of t, which will go to the plant, which is continuous time domain. And this is y of t. This is one configuration also. Now, if you recall here, as we said that E of t, R of t, Y of t are continuous time signals, which means that it's known all the time, while E of k, for example, this is E of k, and U of k is only known at certain time instant. So discrete time system arise if the system involves sampling operation of a continuous time system. So here we can add a note that discrete time signal arise if the system involves a sampling operation of a continuous time signals. So simply, this means that if I'm having here, for example, E of t, I'm having sampler like switch, and this switch is open and closed with certain sampling frequency, which has a period of t, sampling period, and this will be the E start of t, which is the sampled signal. So now we can discuss the discrete time system and the Z transform, and this is actually is chapter 2. So as we said before, the discrete time signals arise if the system involves a sampling operation of a continuous time system. So let's replot the signal. This is E of t. Let's assume that this is the signal of U of t. Now here we have a sampling operation. So we have now the sampled signal, and we will call the sampled signal E start of t. So the sample signal is only appear if the switch is closed, and let's assume that the switching frequency or the sampling frequency has a sample period of t. So if we virtually plot the signal, when the switch is closed, we can see this point, and after another t you can see this point, another t you can see this point. So we are sampling the signal with respect to sampling a frequency. So here at t, 2t, 3t, and so on, where t is the sampling period. So here t stands for the sampling period. So E of t present all the time. This is the t, this is the E of t, this is the kt, and this is the E star of t. So here E of t it presents all the time. It's a continuous time signal. So here E of t presents all the time. It's a continuous time signal, while E star of t, the sample signal, known at certain time instant only. E star of t is only known at certain time. So mathematically, if I need to represent the sampled signal E star of t, so simply now if I need to represent the sample signal, I will use the impulse function in order to represent it. So E star of t will equal E of 0 delta of t plus E of t delta of t minus t capital plus E of 2t delta of t minus 2t capital, and so on, which can be written as the summation from k equal to 0 up to infinity E of kt delta of t minus kt. Now, if we take the Laplace transform of the sampled signal, which is the E capital star of s, which will equal the Laplace transform of E star of t, it will equal to E of 0, the constant, the delta in Laplace is will equal 1, delta t, then plus E of t exponential minus st plus E of 2t exponential of minus 2st, and so on. So, which can be written in compact form as summation from k equal to 0 up to infinity E of kt exponential of minus skt. So now I need to find, let's say, a relation between the sampled signal and the signal in the z domain. So let's take the z transform of E of t. The z transform. So let's take the z transform of E of t. Now we know that E of z, which is the z transform of E of t, which will equal the z transform of E of kt. By definition of the z transform, it will equal the summation from k equal to 0 up to infinity the function E of kt multiplied by z to the power minus k. This is the definition of the z transform. Now, if we compare E of z with E of s, as you can see, if we compare this expression to this expression, they are identical if z is equal exponential of st. So simply we can say that E of z and E star of s is related by E of z is equal E of s star such that z is equal exponential of st. So now we have a direct mapping between the s domain and the z domain. So now we said that E of z and E star of s are related by E of z will equal E star of s such that z is equal exponential of st. So now we can make, let's say, a relation between the s-plane and the z-plane. Now if you recall, in the continuous time system, we have the s-plane. Here's the real sigma, and this is j omega, and this is the s-plane. And we know that in the s-plane, if all the roots of the characteristic equation have a negative real part, which means that sigma less than 0, the system is stable. If at least one root has a positive real part, so this means that if sigma greater than 0, the system is unstable. And we know that if I'm having the boundary here when the sigma is equal to 0, this is the boundary when sigma equal to 0, and if I'm having a simple root, then this will be the critical stable case. So remember that S is complex variable, and now we have a relation between Z and S. So now we have a relation between S and Z such that Z is equal exponential of st. But we know that S is a complex variable, so it has a real part and imaginary part. So simply this means that Z will equal exponential of sigma t exponential of j omega t, which will has a magnitude and angle. In this case, the magnitude will be the exponential of sigma t, and the angle phi will be omega t. So now we have the following cases. If sigma less than 0, this implies that the amplitude of z is less than 1. Now, if sigma is greater than 0, this implies that the amplitude of z is greater than 1. And if sigma is equal to 0, this implies that the amplitude is equal to 1. So simply here, I'm having a unit circle in the discrete time system. I will have, or the z domain, I will have the unit circle. So let's try to plot it here. This 1, 1, 1, and 1. And let's assume that this is my unit circle. So sigma less than 0, which is the left half side of the complex plane, is mapped to be inside the unit circle. Now sigma greater than 0, which is the right half side of the complex plane, mapped to be outside the unit circle. And the g omega x, the case when sigma is equal to 0, is mapped to be on the unit circle. So this is very interesting in such that the left half complex plane in the S plane is mapped inside the unit circle. The right hand side of the S plane is mapped outside the unit circle. The g omega x of the S plane is mapped on the unit circle. So for stability, for example, now I can make a conclusion that in the Z domain or discrete time system, the system is stable. For discrete time system, the system is stable if and only if all the roots of the characteristic equation lie inside the unit circle, and it will be unstable if at least one root of the characteristic equation located outside the unit circle, and it will be critically stable if I'm having a simple root on the unit circle and all the other roots must be located inside the unit circle.